We're going to be looking at some examples of refraction and doing some problem solving involving refractive index. If we consider the refraction of this light ray when it's incident on a glass block and the incident ray is along the normal line, then it will pass straight through the block. There will be no refraction, no change in direction. Also, for this ray of light, it has passed straight through the glass block at this point. And the reason why is, if we was to zoom in at this point, you can see that the ray of light is acting along the normal line, so it's perpendicular to the surface, and so it will pass straight through. If we now consider the refraction of this ray of light, then at this point where the incident ray meets the surface, we need to draw the normal line. So remember, the normal line is 90 degrees to the surface. Now, if there was no change in medium, the ray would pass straight through. However, because the ray of light is moving into the glass block, which is a denser medium, light will slow down, its speed will decrease, so that means it will be refracted towards the normal line. So this line needs to change direction so it's towards the normal line. Now, if we consider the refraction of this light out of the block, again at this point we need to draw the normal line. Remember, that is 90 degrees to the surface. Now, there was no change in medium. The light ray would travel straight through, but because it's now going into air, which is a less dense medium, the speed of the light wave will increase, and so if wave speed increases, the ray is refracted away from the normal, so we would draw a refracted ray in that direction. Water waves travel slower in shallower water. So if the depth of the water changes, so it goes from deep to shallow, then the water waves will refract because there's a change in wave speed. So in this example, we've got water wavefronts, and we're going from deep water to shallow water. And so in order to determine the direction of the refraction of the water waves, we will need to draw a normal line relative to the change in depth of the water. And because the water waves travel slower in shallower water, that means the wave speed decreases. The water waves will be refracted towards the normal line. So if we draw the refracted ray, so it's towards the normal line. And if you remember how we draw the wavefronts, we draw them perpendicular to the ray. So we need to draw the wavefronts so that the incident wavefronts link to the refracted wavefronts. And so what you can see is the frequency of the water waves has remained the same, but because wave speed has decreased in shallower waters and frequencies remain the same, then the wavelength must decrease, and that's shown by the decrease in the spacing between the wavefronts. We're now going to consider the refraction of water waves when it goes from shallow water into deeper water. So again, we first need to draw the normal line relative to the boundary from shallow water to deeper water. As the water waves travel faster in deeper water, that means the wave speed increases, so the water waves will be refracted away from the normal. So if we draw the refracted ray away from the normal line, and then we now need to draw the refracted wavefronts, and they will be perpendicular to the refracted ray, but they also need to link to the incident wavefronts. So our refracted wavefronts will look like this. And so you can see that again the frequency of the water waves remain the same. However, because wave speed has increased as it goes into the deeper water and frequencies remain the same, then the wavelength must increase, as shown by the increase in the spacing between the wavefronts in the deeper water. In this question, medium 1, the incident medium, is water, and medium 2, the refractive medium, is glass. To find the angle through which the ray is deviated as it passes from water to glass, we need to know the angle of refraction. So we need to use Snell's law, where n sine theta equals a constant. So we can use this, where for medium 1, the incident medium, which is water, the refractive index of water multiplied by sine of I will equal, for medium 2, the refracted medium, which in this case is glass, the refractive index of glass multiplied by sine the angle R. As we need to find angle R, we need to rearrange this equation to make sine R the subject. So sine R will equal sine I multiplied by the refractive index of water divided by the refractive index of glass. And if we substitute for I and the refractive indices, we get sine R equals 0.2964. And so to get the angle R, we do inverse sine of this value, which gives us an angle of refraction of 17 degrees. And so the angle of incidence was 20 degrees, and the angle of refraction is 17 degrees. So the angle through which the ray was deviated is 3 degrees. In this question, we have the two speeds of light in the two media and the angle of refraction, and we need to find the angle of incidence. So using Snell's law, sine I divided by sine R equals the speed of light in the incident medium divided by the speed of light in the refracted medium. So the incident medium is medium 1 and the refracted medium is medium 2. And as we need to find the angle of incidence I, we need to rearrange this equation to make sine of I the subject. So sine I will equal the sine of R multiplied by the speed of light in medium 1 divided by the speed of light in medium 2. And if we substitute for angle of refraction and the two speeds, we get sine I equals 0.9304. And so to get the angle of incidence, we do inverse sine, which will give us 68 degrees. And we can see when light slows down, the light is refracted towards the normal so that the angle of refraction is less than the angle of incidence. In this question, as radio waves and light waves are electromagnetic waves, they both travel at the same speed in vacuum, or free space, we can apply the refractive index equation to radio waves. So the refractive index of water for radio waves will equal the speed of radio waves in free space divided by the speed of radio waves in water. So the speed of radio waves in free space will approximately equal the speed of radio waves in air, and speed is equal to then the frequency multiplied by the wavelength, where in this case the wavelength will be the wavelength of the radio waves in air, and the speed of the radio waves in water will equal the frequency multiplied by the wavelength of water. And in refraction, the frequency of the waves remain the same, so F will cancel, so the refractive index will equal the wavelength of the radio waves in vacuum or air in this case divided by the wavelength in water. And so if we rearrange this equation to make the wavelength in water the subject, then that will equal the wavelength in air divided by the refractive index. And if we substitute in these values, that gives us the wavelength of the radio waves in water as 2,256 kilometers.